For evaluating the performance of a metal organic framework or zeolite for a specified separation application, we need experimental data on the unary isotherms of the guest species constituting the mixture. Commonly, the unary isotherms are measured at different temperatures, and this data at different temperatures is also used for calculation of the isosteric heat of adsorption, QST. Today I want to discuss the procedures for fitting the unary isotherms. It seems a trivial subject, but I think it's worthy of careful and detailed attention. And one of the things I'm going to put forward in my presentation today is a philosophy that was voiced by an English Franciscan philosopher and priest in the 14th century, and this philosophy is commonly termed the Occam's razor. Simply put, Occam's razor states, do not complicate things beyond necessity, and I'm going to use this principle in deciding on the proper modeling choice for fitting the unary isotherms for MOFs and zeolites. Let us start by examining the experimental data for the unary isotherms for nitrogen and methane in BARPZ. That stands for barium exchanged reduced pore zeolite. The data is from the paper by Wilkins, published in Industrial Engineering Chemistry Research in 2021. The data are shown here. For each of the guest species, the isotherms are measured at 3 different temperatures: 30 degrees Celsius, 50 degrees Celsius, and 70 degrees Celsius for nitrogen, 30 degrees Celsius, 40 degrees Celsius, and 50 degrees Celsius for methane. Even visual inspection of the experimental data would suggest that for both guest species, the single-site Langmuir model is appropriate. And let's see how the data can be fitted and the isosteric heat of adsorption can be determined from the set of experimental data. For each of the guest species, nitrogen and methane, the experimental data at the 3 different temperatures can be fitted with a single-site Langmuir model, where the Langmuir parameter B is taken to be temperature dependent with the form shown here. B equals B naught times the exponential of an energy parameter E divided by RT. The data at the 3 different temperatures are plotted here, in which the molar loadings are plotted against the surface potential, and the surface potential is a proxy for the spreading pressure, and the expression for the spreading pressure is shown here. If people are interested in the background to the concept of the spreading pressure, watch my YouTube video on the web. The advantage of using these surface potential as x-axis is that the data set for at all three temperatures collapse to a single curve, and the continuous sorted line shows this single site Langmuir fit. We see that over the entire range of surface potentials that serves as a proxy for the pore occupancy, the single site Langmuir is of excellent accuracy for both nitrogen and methane. There are three parameters which determine the fit: the saturation capacity, B0, and the energy parameter E. The energy parameter E, in this case, can be identified with the isosteric heat of adsorption, and therefore the isosteric heat of adsorption for nitrogen is 25.5 kilojoules per mole, and that for methane is 22.2 kilojoules per mole. Now, what I do generally is to choose the isotherm model, in this case the single site Langmuir model, and for each of the guest species determine the three parameters QSAT, B0, and E using the Excel solver. So I choose the model first, and the simplest model to start with, and see if I get a good fit for the entire data set at different temperatures. And in this case, we note that the fits are excellent for both guest species. So the simpler model, in this case a single site Langmuir model, is the appropriate and the best one to use. I summarize in the slide the philosophy that I adopt in choosing the isotherm model for fitting experimental data on the Unary isotherms. Applying Occam's razor, I start with the simplest model, the single site Langmuir model to start with, as shown in the foregoing two slides for barium RPZ. Only if the single site Langmuir model is of inadequate accuracy do I proceed further to refine the model. And then I go one step up and choose the two site Langmuir model with two different sites, and this is required if there are isotherm inflections. For example, if I have adsorption of say normal butane or isobutane in MFI zeolite, where the isoalkane locates preferentially at the intersections, the Unary isotherms show strong inflections that can only be captured by a two-site Langmuir model. So the next choice would be this one, and only if this fails do I proceed further to invoke the two-site Langmuir Freundlich model, where we have the Freundlich exponents nu A and nu B. In very special cases for isotherms of water and some alcohols in MOFs and zeolites, and for flexible MOFs, we may need to even go further and adopt the three-site Langmuir Freundlich model. So the recommended procedure is to start with the simplest model and increase the level of complexity as demanded by the experimental data. I often see in the literature that the experimental data in the unary isotherms at any temperature is fitted using the dual site Langmuir-Freundlich model, even though for that particular guest host system, this is an overkill. I gave an example here of the unary isotherms for ethane and ethylene in a MOF, and the experimental data are shown here and fitted with the DSLF model using commercial software. The commercial software, if asked to fit the unary experimental data, produces 6 parameter values as shown here for ethane, and the 6 parameter values for ethylene are shown in this column. We note that the saturation capacities are unrealistic. 14.002, 4.82, and we see that the experimental data only shows a saturation capacity which is perhaps 5.5 for ethane and 4.5 or thereabouts for ethylene. So asking a software to fit the parameters yields saturation capacities and Freundlich exponents that do not seem to have any physical significance. Indeed, I've taken this data and fitted it with a single site Langmuir model to an accuracy that is acceptable. So the use of a dual site Langmuir-Freundlich model in these two cases is definitely an overkill. But there are also serious consequences on using the dual site Langmuir-Freundlich model, because extrapolation to lower pressures or higher pressures than in the experiments is fraught with danger, because the extrapolated values are crucially dependent on these Freundlich exponents. So the conclusion I would like to draw is that only introduce the Freundlich exponents and the additional sites if it is strictly required. Use Occam's razor and choose the simplest model and increase the degree of complexity of the model only if the data demands it. Let's examine the experimental data for the unary isotherms for propyne and propene in ZnU2. ZnU2 is TIF6 copper TPA, and the experimental data are taken from this publication. The data for both components show isotherm inflections, and certainly for propyne, the isotherms are also rather steep, and the single site Langmuir model fails to capture the isotherms for both guest species. The dual site Langmuir model also fails, and we need to resort to the dual site Langmuir-Freundlich model. Now, what I generally do is to fit the data at the 3 different temperatures simultaneously using the Excel solver. Let's see how we do that. Let's fit the experimental data at the 3 different temperatures using the dual site Langmuir-Freundlich model. Now, the parameters BA and BB are taken to be temperature dependent, with the energy parameters EA and EB. So for each guest species, there are 8 parameters to be fitted. QA sat, BA naught, EA, nu A, QB sat, BB naught, EB, and nu B. I determine these 8 parameters simultaneously using the Excel solver. But I do not do this blindly, because I want to ensure that the parameter values are realistic. And if I use the Excel solver, I have the freedom to choose the saturation capacities such that the values are realistic. For example, for propine, the fitted parameters are shown here. You note that the QA sat value is 6, then the QB sat value is 2.5. If you add them together, we have a saturation capacity of 8.5, which seems to be reasonable because that is what the experimental data shows. The graph here plots the molar loading as a function of the surface potential. The surface potential is the proxy for the spreading pressure, and for the dual site Langmuir model, the analytic expression for the surface potential is derivable and is shown here. The advantage of using the surface potential as x-axis instead of the pressure is that the entire data set at 3 different temperatures collapses to a single curve for both guest species. And this is a convenient way to see if the fits are of good accuracy and representative of the experimental data. Also look at propene. We see that saturation capacity fitted is 4.4 and 2.1. If you add them together, we have 6.5. That's about correct. So we get realistic values because we can, in using the Excel solver, we can ensure that the fitted parameter values are realistic. Note also that I have here chosen the second Freundlich exponent nu B to be unity in both cases, because perhaps only one of the Freundlich exponent needs to be different from unity. And we note also here that nu A value is 1.24 and nu A value for propene is 1.3, close together. So fitting the isotherm data with Excel ensures that we get physically realistic fit parameter values that allows safer extrapolation to lower pressures than measured experimentally in the isotherms. Such extrapolation is important for C3H4, C3H6 separations because the feed mixture may contain only 1000 ppm of propine, and we need to reduce the propine content to less than 40 ppm. A further advantage of fitting the DSLF model with temperature dependent parameters is that the isosteric heat of adsorption can be determined by analytic differentiation of the isotherm parameter fits with temperature dependent BA and BB parameters, as we shall see in the subsequent slide. From the dual site Langmuir-Freundlich fits with temperature dependent BA and BB parameters for propine and propene in ZnU2, we can determine the isosteric heat of adsorption using this expression by analytic differentiation of the DSLF model. The analytic differentiation can be carried out using Mathematica or Maple and can be easily programmed in Excel. The calculated values of the isosteric heat of adsorption for propine and propene are shown here using the fit parameters for ZnU2 as shown in the previous slide. This data has been published in this paper. For fitting unary isotherms, we need to adopt the Occam's razor. Do not complicate things beyond necessity. We start with the simplest physical model, the single-site Langmuir model, and only resort to more complex models such as the dual-site Langmuir model or the dual-site Langmuir-Freundlich model if the unary isotherm data cannot be described adequately using simpler models. For example, isotherm inflections require the recognition that there may be two different sites for adsorption within the MOF framework. If the isotherms show steepness, such steep isotherm behavior requires the Freundlich exponent to properly capture them. Such is the case with flexible MOFs or with guest molecules that undergo molecular clustering. The isotherm data at different temperatures can be fitted simultaneously using temperature dependent parameters, and the advantage of this approach is that the T-dependent parameter model can be differentiated analytically to determine the isosteric heat of adsorption. Once the isotherms are properly fitted with the appropriate physical model, then the adsorption selectivity calculations can be carried out, and for this purpose you may watch my YouTube presentation on the IAST.